each time. So let's start the 42nd ASE seminar. So first of all, so welcome to the 42nd ASE seminar. It's an advanced environment, advanced supercomputing environment. So my name is Kengo Nakajima from University of Tokyo. And first of all, I'm very happy to invite all of you to this in-person meeting. So this is the first in-person ASE meeting in recent 3 years. So at the beginning, I'd like to briefly overview the history of these meetings. So my former colleague, Professor Takahiro Katagiri, he's now in the Nagoya University, this guy. So he started this series of the ASE seminar in March 2008, 15 years ago. So ASE seminar is held irregularly when we have visitors to our centers. And the other speakers are not necessarily limited to faculty members of our centers. And the official language is not fixed. So today it is in English. And the first one was March 3rd, 2008. And any topic related to HPC and supercomputing. And last on-site meeting was for this seminar on February 4th, 2020, 3 years ago. And the last online one was the 41st seminar on February 4th, the same day on the 2022. And this is the first hybrid ASE seminar. Today's our guest speaker is Dr. Jonathan Carter from Lawrence Berkeley National Laboratory. And also we have a guest student speaker, Sheena-san. He's a PhD candidate of the Graduate School of our universities. And this meeting today is organized by our Information Technology Center and also JCAHPC. So JCAHPC stands for the Joint Center for Advanced High Performance Computing. It started 2013. It's a collaboration between University of Tsukuba and University of Tokyo. The purpose of this consortium is the promotion of the computer science, design and procurement and operation of large-scale systems. As you may know, so we operated Oakforest-PACS. It's the first system of our consortiums. And so this is a very nice system with Z05 and retired 1 year ago. And so in certain durations, so this worked as a national flagship system between K and Fugaku. And now we are doing the procurement of the successor of the system. So it's called OFP2. So this is today's program. So I start some introduction of this center. And so our speaker, invited speaker, will talk about the future of the Berkeley Lab. And the third one is about the successor of the Oakforest-PACS OFP2. And we have a talk by Sheena-san and end that. Okay, so let's start my talk. It's an innovative supercomputing by integration of simulation, data, and learning. I believe many of you heard about this talk before. Okay. So first of all, I'd like to thank my sponsors. And so this is the overview. So I start with the hardware on the first floor of this building and software and some applications and some future perspective. So this is some introduction to Dr. Carter's talk next to me. So this is the history of our supercomputers in this century. So basically, so we are operating two big systems. So lifetime is 6 years for each one. So this means every 3 years, so we have a new systems in the beginning of this century. But recently, we have some gaps. So mainly because of some vendors issues. So sometimes we have so many systems, but now we are operating two systems. So we have nearly 3,000 users, and more than half of them are outside of the University of Tokyo. And recently, so we have some systems with green tags, so with GPUs or accelerators. And currently, we are operating the Oak Bridge CX. It's based on the Cascade Lake system. It's not so new, but it's very nice systems. So another one is today's main issues about Wisteria VDX on this first floor. I'll talk about this in detail later. So this is a research area based on the CPU hours. So in 2 years ago, at that time, we have 2 systems with a general purpose CPUs and 2 GPU clusters. And you can see so very different usage. Okay, our traditional usage area for the supercomputers, so engineering, earth and space science, and material science, and physics. But you can see for the case of this GPU cluster, so we have a very different cards, such as AI, bioinformatics related to the genome analysis or medical image recognition using machine learning. So it's a very new emerging areas of usage. So if you think about the future of the supercomputing, so we have various types of workloads, computational science and engineering, it's a simulations and big data analytics, AI and machine learning. So integrations and convergence of these 3 categories, simulation, data, learning. So we call this S+D+L, is important towards Society 5.0 proposed by Japanese government. As you may know, the Society 5.0 is a super smart and human-centered society by digital innovation, such as IoT, big data, AI, etc., and by integration of cyberspace and physical space. So this part is very important, and it's identical with the idea of the digital twin. So we have a BDEC project, stands for the Big Data and Extreme Computing. So we are trying to construct a platform for integration of S+D+L. But here, we are focusing on the S, simulations. Okay? So we try to make a sophisticated simulations with the support of the data and learning. So this idea is called AI for HPC, AI for science, or digital twins. So this plan started 2015, 8 years ago. And 2 years ago, May 14th, 2021, we started to operate our new system. It's called Wisteria BDEC 01. So this is the first BDEC system, and it's a platform for integration of S+D+L. So this is a Fujitsu system. The total peak performance is 33 petaflops, and the aggregated memory bandwidth is 8.38 petabytes per second. And we have 2 types of the node groups. One is simulation nodes called Odyssey. It's based on the Fujitsu's prime HPC FX1000 with the A64FX ARM architectures. Total peak performance is nearly 26 petaflops. And it's a commercial version of the Fugaku system. So it's the size is 120. So another part is the data and learning nodes called Aquarius for the data analytics and AI machine learning workloads. So it consists of the 360 so NVIDIA's A100 GPUs and 45 nodes of the Intel Xeon Ice Lake. And some of the data and learning nodes are connected to the external resources directly, and we can import observational data from sensor networks or some external servers. So this is a ranking of the last SC November. And the score is separated for the Odyssey part and Aquarius. And now it's 23rd in the world. So this is how we utilize these systems. So as I mentioned, so we are focusing on the simulation part. And so as you know, real world simulations are nonlinear, and we need a lot of parameter studies. So our primary purpose is accelerating these cycles to make these parameter studies by support of the data simulations and machine learning for the optimization of the models and the parameters. Okay. So this is a hardware, and we are also developing the software called H3 Open BDEC. And this is a 5-year project, and it started in 2019, and this is a 5th year of this project, and this is supported by Japanese government. And so PI is myself. So these are the main members of these systems. We have a wide range of the experts: computer science, computational science, numerical algorithms, data science, and machine learning. So some of them are from the University of Tokyo, and so some of them are outside. Okay. So this is a structure of the software. So we have 3 innovations. One is a new principles for the numerical analysis by adaptive precision, automatic tuning, and accuracy verifications. So we are trying to utilize the low precisions and adaptive precisions and the mixed precisions for the computing. So this is one of the results by my former colleague, Dr. Kawai, and he developed FP21 and FP42. So they are the mid of the FP64 and FP32 and FP16. And this is very efficient and also very accurate and robust for ill condition problems. The second part is the integration of the S plus D plus L by hierarchical data-driven approach. So this is a utilization of the machine learning for the simulations. So this is a results by my colleague, Professor Shimokabe. So he's in this center. And our motivation is trying to accelerate the transient CFD simulations. So by predicting the 10 times steps ahead from the current one. So by this, we can accelerate the CFD computations. So in some cases, we have a very nice result. So another example of the integration of the machine learning of the simulation is this is my also the former colleague Professor Shiba. Okay. He just left our center this in the end of this March, and he's a specialist of the molecular dynamics, and he introduced a graph neural network to accelerate the very accurate simulations of the molecular simulation of the glass materials. Okay, so I'll talk about another part. So we have a third pillar of this our project is a software and utilities for heterogeneous environment such as Wisteria VDEC01. So I'll talk about this part with some applications. The most important one is the 3D earthquake simulations with real-time data observation and assimilation using the real-time observational data. So what we are doing here is trying to make accurate wave propagation simulations for the seismic wave utilization of the real-time observational data by JDXNet. So next page shows a very brief overview of the JDXNet. And so we have a seismic observational data, more than 2,000 points in Japan, and it provides 100 hertz. That means 100 times per second. And so this is available through SciNet in real time. So the data size is corresponding to the 400 or 500 gigabytes per day. And so yeah, we can get the data, including some satellite observations, real time. So we try to utilize this data to make accurate simulations of the seismic wave propagation. So this is the overview of our method. And if we have a earthquake, and we start the wave propagation simulations, and so we also correct the result by utilization of the observational data in real time. And so first 50 or 60 seconds, we are doing both of the assimilations and simulations, and then switch to the pure simulations. So as a part of this data assimilation part, we are using the very simple method, like this way. And so we do the simulations in the later stage. So next, several slides show the examples about the of Niigata 2007 earthquake. So this is the epicenter, it's Niigata, and this is Tokyo. It's roughly 200 kilometers away from the Tokyo. And in this so-called Kanto area, we have 350 observational points. And we try to combine the simulations and observation from these points. Okay, so next page shows a result. And so this right-hand side shows some comparison of the observational result at this Tokyo point and some simulation result. I think. So if you switch from the simulation plus simulation very earlier, you can see that the results are very different from the observations. But if you put the 50 seconds, so you can get very nice and accurate result. Okay, so in order to do this, we developed a software for this system. So if you want to do this type of the computations, so Aquarius part, so data and learning part with the GPU cluster is doing the filtering of the observational data and the visualizations of the result. And the Odyssey part, this simulation nodes with the A64FX is doing data assimilations and simulations. And we need a transfer between these two nodes. But actually, combining the two nodes groups, Odyssey and Aquarius, is so difficult or impossible because a single MPI job over Odyssey and Aquarius is not possible because they are different architectures. But so these two parts are connected through InfiniBand EDR network with a 2 terabyte parsec. It's a very rich network. And we developed a software. It's called the H3 OpenSys Weight IO socket and H3 Open Util LP. So I start from this so-called Weight IO software. It's a library for interprocess communication through InfiniBand EDR with MPI-like interface. Okay, so next page shows the application providing interface for this Weight IO socket. And yeah, instead of calling the MPI iSend, we can call Weight IO iSend from Fortran and C, and we can write a program very easily using the C or Fortran programming language. So this is developed by my colleague, so he's sitting here, Professor Sumimoto. Okay, so this is a same figure. And this is a real system which we developed. So actually, the earthquake itself occurred 15 years ago. And we just put that data at the external server, okay? And we just get these data from outside and importing that part from our Aquarius part. And doing filtering and sending the filtered data to the this Odyssey part, and they are doing computations. And the result for the visualization is going back to here, and so they are doing the moving. So this is cycles. So next part shows the communications by Weight IO socket for this sending filtering data from the Aquarius to the Odyssey. So this is a program written in Fortran from the Aquarius. And you can see we have a lot of Weight IO iSend, okay? And this is the receiving part for the Odyssey. So we have several lines for the Weight IO I receive. So this is how we write the code. So next slide shows the future directions towards integration of S+D+L for this earthquake simulations. So primary purpose is try to do the accurate prediction of the seismic wave propagation with real-time data observation and assimilation, which I mentioned. And we hope this is very useful for emergency information for safer evacuations. So actually, so we are applying the very simple 3D finite difference code, and 10 times faster than real phenomena is possible with 1,000 or 2,000 nodes of our modern supercomputers. So it's a very realistic. So another purpose of this system is trying to develop a 3D underground model. So actually, 3D underground model is a very heterogeneous, and the observation is very difficult. It's a very deep. And inversion analysis of the seismic waves are important for prediction of the structure of the underground model. And we think that machine learning may be utilized for acceleration of this prediction based on analysis of the small earthquakes in normal time. So magnitude is less than 3.0. The Niigata earthquake is magnitude is nearly 7.0. But so as you know, 3.0 or 4.0 size earthquakes occurs in Japan almost every day, unfortunately. And we can utilize that further. And we need a more sophisticated data assimilation method, such as a 4D bar. But actually, we discussed with our expert, and construction of the 3D underground model by this model in the previous page for a long period seismic wave propagation is not realistic, because the mesh size is too big and it's very difficult to capture the feature of the material. And we are trying to develop different types of the models. Local model with smaller meshes should be used. And we have such a observational network, and we try to develop the underground model utilization by such types of the observational systems. Okay, so next one is the HPCI AI workload combinations. And this page shows H3 Open Util MP. So we are developing a coupler. Okay, traditional coupler is a weak coupling tools for multiple applications, usually two: structure and fluid, or atmosphere and oceans. And each application does a single computations. But our new coupler provides a very sophisticated features. So I just go to the next page. So this is one of the features, new features of the couplers. So there are couplings, simulation workloads and AI workloads on the Odyssey and Aquarius. And so it's connected through this InfiniBand. The first version of the coupler developed in the 2021 May, that was based on the MPI, and it's on the homogeneous systems. But by combining with the weight.io library, which I mentioned in the previous part, we developed a new coupler, so that provides a capability for coupling the workload on different architectures. And since last year, June, so we can use this on our system. So one of the examples is some global cloud simulations. Okay? So in this type of the simulations, we are utilizing two types of the models. One is a very detailed models for the high resolutions. So another one is a very coarse models. So this part is called parameterization. So in order to get the parameters. And 75% is spent for this detailed model, and 25% is for this small part. And our motivation is trying to replace this part with AI. Okay. So we are implementing this detailed model on the Odyssey and this part on the Aquarius. And so through this coupler and weight.io, and trying to reduce the computation time just for the predictions. So this is some experiment, very preliminary experiments. And here, input is so density, internal energy, and so this is a vapor density. And we try to estimate the so gradient in time directions. And we applied a very simple machine learning tools based on the PyTorch, just a 3-layer perceptrons. And so we get a very nice result in the next page. So this is the input, okay? Density, energy, and the density of the vapor. And this is the result of the simulations, okay? And this is the prediction by the machine learning. So although the peak is not captured clearly, but so the general features are very nice, and we can utilize this type of the approach for the real simulations. Okay, so next page shows up so from the viewpoint of the operations. Okay, and we have almost 8,000 nodes of the Odyssey and 45 nodes of the Aquarius. Odyssey is not so crowded, but Aquarius is very, very crowded. Okay, and our current strategy is one node, a single node of Aquarius is reserved for this type of workload on the integration of S plus D plus L. And two separate jobs should be submitted. And if both jobs grab resources, execution starts. Yeah, the problem is that from this year, so we have a lot of these workloads, and so we need a more sophisticated strategy. So next page shows two separate examples of the scripts. Okay, and so far we have very nice jobs for developing the software and job submission systems. The problem is the policy of the operations, and we need a more flexible and complicated policy. Okay, so this is a summary of my talk, and I have some additional pages for the future works. One is the more applications, and another one is the next generation supercomputing. So it's an introduction to the next talk. So as for the extension of the applications, we are trying to do the international collaborations with some European institutes such as Itoyori, some Croatian institute, and so German university and CA in France. And this proposal for the JCAHPC has accepted for this year's work. And we are trying to extend our applications to some so regional earth science problems, and also some material science, and such as chemistry and physics. And also we are developing a system for the so based on the uncertain quantification of the extreme weather prediction by my colleague, Dr. Sawada. And also this is a prediction of the marine ecosystem. So this is a real ecosystem. So trying to predict the position and size of the fish schools. Okay? So this is for the some this kind of the industry. So this is a collaboration with Riken University of Tokyo, Osaka, and Tohoku universities. Okay, so next generation supercomputers. So near-term issue is so talk by my colleague Professor Hanawa about the OFP2. And as for the long term, and so yeah, if you want to continue sustainable development of the science and technology, so integration of three categories is essential. So this is my personal point of view. And if you want to integrate these, the architecture should be somehow heterogeneous. So one example is our Wisteria VDX01. And for example, in Europe, Germany, so they are also developing some modular supercomputing architecture, so combining several systems. But so we developed the weight IO, which I mentioned in the previous part, and this can be extended for internet or cloud, and so using several architects like this. So this is the comment of the quantum computing. So this is my personal point of view, and Jonathan will talk about this in the next part. And I think it will take many years until the real quantum computers are in practical use. And everybody agrees that modern supercomputers are not replaced by quantum computers. And we should think about the utilization as some kind of the accelerators. And what we need to do in next 30 to 50 years is finding appropriate applications for quantum computers and utilizing the simulators on supercomputers and quantum-inspired devices such as digital annealer, and preparing the software and programming environment for combining supercomputers and quantum computers. So probably this is not so far from the general ideas. So I think the weight IO is also possible for this combining the AI chips and the quantum computers. So we try to develop our systems for this future systems. Okay, so I think we don't have enough time, and I should stop here. Okay, thank you very much for your attention. Okay, so let's go to the next part. And I would like to introduce our next speaker, Dr. Jonathan Carter. So I found that this recent picture, but this is not so good. Okay, okay, okay. But anyway, so it's a very recent one. Okay, so he's an associate laboratory director for computing science and the Lawrence Berkeley National Laboratory from 2020. So he was born in Manchester, UK, and I heard he preferred Manchester City to Manchester United. And he received his PhD degree in chemistry from the University of Sheffield, UK. And before joining Lawrence Berkeley in 1996, he worked for IBM and the University of British Columbia. And in the first 15 years in the Lawrence Berkeley National Laboratory, he worked for the National Energy Research Scientific Computer Center, NERSC, and as a user services group. So I believe this is a third appearance in the ASE seminars. So welcome back. And the title of his talk is Future of the Berkeley Lab Computing. And so if you extend these numbers, he will be back in 2030. Okay, so let's welcome our keynote speakers, Jonathan Carter.
Good afternoon, everyone. Great to be here. This is my first international trip since the beginning of the pandemic, and I do have to apologize for that photograph. Is it? Here we go.
How about that? Okay, sorry about that. Yeah, I'm delighted to be here. It's my first international trip since the pandemic, and it's great to be here again and participating in one of these seminars. The photograph was designed to make me look mean and ferocious, so that my colleagues wouldn't come and ask me for money. So that's my excuse. So I'm actually going to tell you a little bit more about the current state of Berkeley Lab computing, as well as what I think the future might be. And to kick off, I'd like to thank the Department of Energy for its sponsorship. So just a few little things about Berkeley Lab. It's located in Berkeley, California, in the San Francisco Bay Area. It's located right next to the University of California, Berkeley, where we have a lot of joint faculty, people who can work with us. We get a lot of graduate students and so on and so forth who can come up the hill from the campus and work with us. So we've got about 3,500 full-time employees, And last year, the budget for the whole lab was about just over $1 billion. So this is my piece of the lab that I'm overseeing. There are 4 pieces in it. Sudeep Dosanjh is in charge of NERSC, which is the High Performance Computing Center. Inder Monga is in charge of the networking division that connects together all the national labs. And peers, oh, thanks. Peers with all the other academic networks. And then we have 2 research divisions. Stefan Wild recently became Division Director of Applied Math and Computational Research Division. Stefan joined us from Argonne National Lab, and he replaced David Brown, who some of you may know, who retired. And then Deb Agarwal leads the Scientific Data Division. And I just put 3 pictures here that kind of capture some of the challenges that the whole computing sciences area kind of faces. One of them is what I'm calling innovative computational technologies, and that's really how do we adapt to faster networks? How do we deploy them? How can we co-design them with vendors? How do we deal with software challenges that result from that? And then I think picking up really on some of the things that Kengo mentioned, we have 2 other challenges. One centered around machine learning and acquiring the data that is required to make modern machine learning algorithms trainable and useful. And another one is a little bit more specific to the Department of Energy, and we call that super facility, because the Department of Energy, as well as operating high-performance computing centers, it operates a lot of other centers. So it's a little bit like RIKEN in that sense. It operates a light source, it operates a neutron source, and many other besides. And we think a closer integration of all those facilities together would really help with increased scientific impact. So I'm just going to say a few words about this first topic here, innovative computational technologies. So I think many of you know quite a bit about NERSC. I'm just going to kind of skip quickly over here. NERSC is the center for all the DOE's high performance computing needs. So if you have a research project, there's a tool associated with any of the physical sciences, really you can be awarded time at NERSC. So it has a lot of users, about 7,000 or so at the last count, and a lot of different projects. So here's a timeline, again, very similar to a timeline that Kengo showed earlier, of NERSC machines since 2013. And this slide also makes me realize that I'm old, because I was the project leader for a computer back here that's not even on the slide anymore. That was the Hopper computer back in 2010. So Perlmutter is the latest system deployed. It's AMD CPUs and NVIDIA A100 GPUs. It's about 7,500 GPUs in the system. And I believe it's about number 7 or so on the top 500. So it's integrated by HPE, and in many ways very similar to the system you have on the floor downstairs, except it uses a slingshot interconnect instead of InfiniBand. And so the question would be, what is NERSC 10 going to look like? And we anticipate, if the budget is okay, that will arrive in somewhere around 2026. So I'm not allowed to say a lot about NERSC 10 because the RFP is still being developed, and the people who are the project leaders would get very upset with me if I said a lot, but I can say a few things about it. So we anticipate that it'll be about 10 megawatts in power, maybe a little bit more. So we'll have to do some upgrade work on our current building, and as well as doing some other kinds of floor extensions and that kind of thing. We expect it'll cost between $80 and $185 million. And we expect it to use up to 20 megawatts, and we need to install an extra 10 megawatts of power. And so this is the schedule we're shooting for at the moment. going to relieve the RFP later this year. So perhaps more interesting than just those facts and figures is picking up really again on some of the themes that we heard in Kengo's talk. So the idea that the computer is becoming bigger and it's touching more things, so to speak. So the Cori system, which was the last system, was kind of a very classic high-performance computing system where you could just do a little bit of customization with the network in the nurse center, but not very much. And then with Perlmutter, the current system, we have much more tight integration between the community file system, the archive, the network within the building, and also we have a kind of our own kind of like mini cloud system that can be used to run jobs which are more appropriate for that. And then it stretches out a little bit further towards the network, but we expect with NERSC 10 that we want to have some provision to accommodate the other kinds of OSCAR facilities, the other DOE Office of Science facilities that I mentioned, like light sources. We expect we might be able to couple with a commercial cloud and many other things. So we reach deeper into the network of connectivity. So that'll be interesting to see how this project proceeds and what the team decides to build out. I want to say a few words about ESNet 6. Before I took this job, I didn't really know a whole lot about networking at all. I viewed it like plumbing. I provided I could get water out of in my sink. I was happy, and the water went away. I didn't really think much more about it, but I've been trying to learn more about networking and about the interesting things one can do with modern networks, like you can reserve channels on the ESNet network, so you can guarantee quality of service from one site to another. And in that way, if you have a really big transfer that you know is coming, for instance, ESNet now has a transatlantic link. So several links here go over from the east coast of the US to Europe and to CERN. And so if you have a very big particle physics data set you want to move from CERN, it's a good idea to reserve bandwidth. And at the same time, ESNet has a bunch of tools that they call the Science DMZ for Demilitarized Zone, which enables you to run a secure and yet performant channel, so you don't get slowed down by things like a lot of firewalls and things like that. ESNet has generations of networks, just like NERSC has generations of computers. Started off back in the 70s, where it was a very, very limited and primitive network here. And slowly, we've been going through iterations where we've upgraded the whole fiber footprint across the US. And the latest network, ESNet 6, which was actually completed, this slide I need to alter that, TBD to 2023, where this was a completely new network. We leased cable from actually Level 3, which is a telco company in the US. And ESNet lights that fiber up themselves and runs all the switches and routers across it. It's very performant. So some of these thicker links here are terabit plus per second, and then we have slightly smaller bandwidth links according to where the site is provisioned. So up in California here, we have a lot of sites in and around the Bay Area, Sunnyvale, up to Livermore, ourselves, and Slack. And then wherever there's a DOE national lab, we have a very fast pipe to that. And I know Kengo has a fondness for Texas, so I have to point out that Houston has a very good link to it's our fastest site in Texas. This project was completed during the pandemic, and a great deal of work from a lot of contractors and by the ESNet staff themselves. That was 15,000 miles of fiber across the whole continental US that was installed and illuminated. So I was really very happy that project ended with completion earlier this year. So I want to say a few words about Exascale Computing Project. I think many of you will know this is a DOE project, started in about 2016, is finishing really later this year. There'll be a little bit of project wrap up in the next calendar year, but it was to develop a lot of different applications across all kinds of different domains and software tools that would allow them to be run in a transparent and performant way across different architectures such as Perlmutter, the Frontier system at Oak Ridge, and the Aurora system at Argonne when that goes into production. And a highlight, perhaps many of you will have seen if you were at the Supercomputing conference last year, was that one of those applications, Warp-X, here, they managed to win a Golden Bell Prize here for developing this code, which models basically tabletop accelerators using a particle and cell approach. And some of the this was done by people working all across the lab, but the computing sciences contribution was mainly the adaptive mesh refinement portion of that, which is a specialty of many of the applied mathematicians who work with computing sciences. So I wouldn't really be complete without mentioning something about quantum information science and technology, because that's been my own area of study for the past 5 or so years. And the lab has several programs, obviously, in QIS. The program I'm most involved with is the Advanced Quantum Testbed, which is developing new kinds of superconducting qubits. You'll be aware that IBM has a quantum computing platform based on superconducting qubits. So does Google. So do several other research groups across the world. So this is focusing on different architectures other than, say, transmons, things like that. We also have a quantum networking testbed, where the idea is that quantum networks will be useful for connecting together, say, small chips of superconducting qubits, or you might connect a quantum sensor with a quantum computer. And there are some very rudimentary experiments that show how you can make fewer measurements and they can be more accurate with that kind of setup. Also to pick up on a theme that was mentioned previously, NERSC is thinking about how in the future both people will want to come to NERSC to model devices such as these, or develop quantum programs and test out error models and things like that. And then how might eventually one of these devices, which is a bit more productized, how would that be integrated into a regular HPC device or system? So my outlook, kind of like a weather forecast, some clouds, but some sun too, for our outlook for innovative computing technologies. DOE are promising to sustain the Exascale software ecosystem, the applications and software that was designed in ECP. The NERSC plan is well underway, which is good. But then there are some questions that I feel are not entirely clear, that the future is a little bit cloudy or foggy. And Kengo mentioned this also, that will computational science in the future, will it merge traditional modeling and simulation and data-driven techniques such as machine learning? And it seems, the answer is it seems that it will. And I think the road to that looks complicated, but hopefully with a lot of interesting and fruitful challenges. If you just want to focus on traditional computing, is there a path to Zetascale? Does Zetascale even make any sense? I've been engaged in an effort with Oak Ridge and Argonne to look at what kinds of performance predictions we might get from the vendors who might bid on future procurements. What do they feel about Exascale system? And I would say that it's very cloudy. Not really many vendors see a path to such performance. And maybe we'll be able to get to effective Exascale by using AI and exascale machines. And then what role will things like quantum play in the near and the midterm future? I mean, all of that depends on the performance improvements in quantum and whether we can get error correction under control. But that's going to be a fascinating thing that will occupy us in the near and long-term future, I think. Let me just say a few words about the learning and super facility challenges combined. So computing sciences does a lot of work to help the rest of the lab here. So engaging in the mathematics of neural networks, designing more customized AI architectures for things like materials property prediction. We're also involved in automation. I think many of you will know that in a lot of modern labs, there can be robots that do synthesis, that do biology experiments and take data. And how does one interact with those things from a computational point of view? We also curate and deal with the data lifecycle from a lot of different data sources. We have things like they're like modular greenhouses, so you can grow 1,000 plants in a similar environment, but with different nutrients, and take, say, hyperspectral imaging of the plants to see how they're performing, and how do you digest that kind of data? And then a lot of very well-established data sets that are housed in the computing sciences area, such as the DOE's Joint Genome Institute, where it has lots of genomes, primarily from plants, microbes, and fungi. I'll just skip this one because I think I'm running a little low on time. Here's an example I picked because it has this really, I think, this lovely graphic. This is an example of working with GE Research. So GE are making lighter turbine blades for jet engines, and they use this substance called ceramic matrix composite. And this composite is bonded to a larger body of material, silicon carbide matrix, and it's fused in there. And it's not a good idea if the turbine blade breaks apart when it's under stress. So they want to make sure that these strands are very well fused to the silicon carbide substrate. So we developed a pipeline here where we use basically soft X-rays to do micrographs to develop images, and then an AI algorithm picks out gaps in these threads and identifies them. So you could imagine that GE would be able to build a pipeline here to examine when a turbine blade was good or when it would be, have a short lifetime. Sorry, this is kind of a very messy slide, but it tries to speak to the future of an integrated research ecosystem that DOE has in mind. So if we just kind of focus on this is the systems at Argonne, Oak Ridge, and Berkeley. Those are the principal computing sites within the DOE. And then you could imagine that there might be data centers as well, just primarily holding large amounts of data. And we're connecting these to the 28 other experimental user facilities that are in the Office of Science, from synchrotrons to neutron sources, etc. And the idea here is to make it easier for, say, a chemist or a physicist who doesn't know an awful lot about software integration to be able to take their data from one of these sites and use the most appropriate resource in the DOE computing infrastructure and gain insight from their data. So I don't know exactly what it's like in Japan, but in the US, the future of AI is very, very complicated, because obviously AI is a technique that is being deployed quickly, and it has societal impacts and also has a lot of geopolitical relevance. So, who in the world will win, as it were, the AI race? So there's a lot of national planning going on, which is very complicated. And the DOE has been doing a lot of planning. Back in 2019, it had some town hall workshops where it got people together and tried to produce a plan. And this last summer, I've been working closely with my counterparts at Argonne and Oak Ridge, also to develop a plan that we can really present to DOE and have a coherent strategy for the department to move forward in AI. So here it's a bit more cloudy, right? In one way, the project to integrate DOE's current resources is well established and it's underway. But for AI, as you all know, the field is growing and changing really, really quickly. There are many impacts specific to science that are being made, but many more are being made, generally in generative models like ChatGPT 3, 4, whatever comes next. And it's honestly, I find, quite difficult to separate or explain what the value proposition for AI for science is when there's so many breakthroughs coming out of the commercial sector. And as I mentioned, there's a very complicated government policy overlay for us to do with privacy, to do with discrimination, and geopolitical concerns. So here, I'm really much less certain of what the future will hold. I hope that we'll be able to tie together DOE's experimental resources together and use AI as an effective tool to make scientific impacts. But that is, I think, a little more to be determined. And at that point, I think I'm going to stop for questions. Thank you very much for listening.
So next talk is by my colleague, Professor Hanawa, and he will talk about the OFP2. It's a successor of the Oakforest-PACS.
Thank you very much. So I'm going to talk about our next supercomputer system as a JCAHPC, Oakforest-PACS 2. So here is the overview. And so already, Professor Nakajima mentioned that, so I introduced our JCAHPC to catch up the original schedule. So actually, so before the retirement of the Oakforest-PACS system, so in our center, so we are starting to discuss to continue our challenge for the next generation of Oakforest-PACS. So so actually we named the Oakforest-PACS 2 as a successor of Oakforest-PACS. And so I would like to change the actual time, but yeah. So now we are starting the procurement for Oakforest-PACS 2. Yeah, this is statistics of the Oakforest-PACS usage. So actually, the Oakforest-PACS operated during the 5 and 5.5 years. So yeah, so the first 2 years, so very big users are from the energy and physics users, especially the QCD. So the Oakforest-PACS was a nice landing system, and actually the QCD person comes from the University of Tsukuba, and in the University of Tsukuba, so KEN-C system was installed, so named COMA. So these guys are sufficiently prepared for the KNL system. And so gradually increasing the data science or the data simulation users. So and so I would like to talk about the trial for the severe rainstorm experiment, and also the earth science users are increasing from the this is since K computer was decommissioned that time frame, so the many users come from the K computer to the Oakforest-PACS systems, and also the actually this time frame. So we performed the severe rainstorm experiment for the Tokyo Olympic Games, and also the finally the QCD portion is dominant again. And so many users for the Earth and the space so moved to the Wisteria BDEC01 system, new system installed in this time frame. Okay, and so I would like to introduce one impressive result on the Oakforest-PACS usage. So for the Tokyo Olympic Games, so we planned real-time prediction of the severe rainstorm. So in the Saitama University, so we have a multi-phase array radar, and this radar can observe the metropolitan area, and sensor data frequently transferred to the Oakforest-PACS system, and the Oakforest-PACS calculated every 30 minutes to the every 30 seconds for the 30 minutes forecast. And so finally we issued some alert for the severe rainstorm. So actually, this experiment done at original Paralympic Games, and so the successfully finished. And so actually Olympic game was done in 2021, but in that time frame, the already Fugaku system can be used. So this system worked on the Fugaku system. But so this is a very useful for the test for the actual Olympic game. And also the 2020, so that we faced COVID disease, and so the Japanese government quickly called the urgent call for the fighting against COVID-19, and so the 6 project accepted to use our systems, and the most famous one is Professor Tsubokura, the virus droplet infection simulation. The name is for the Fugaku, but so actually in that time frame, Fugaku was the test phase. So actually, I heard that they use very much the Oakforest-CX system. Okay, so I would like to skip. And so and this is other statistics in our center. So in the 2021 timeframe, we had a various kinds of systems, 6 kinds. And so green shows GPU clusters, and blue shows multi-core or many core systems. So as you can see, it's a very different kind trend for the users. So multi-core or many core system, traditional CSE users are the dominant, but also in the GPU system, bioinformatics and also the AI, actually, bioinformatics uses medical image, like a medical image recognition with deep learning technologies. So as you can see, that quite different kind of users use their preferable system. Okay, and we would like to enhance that our users so that we need so these we would like to promote for these kind of very wide range users, and so so the third, second generation system, Oakforest-PACS 2. So this is also history so far for the Oakforest-PACS 2 procurement. So we already decided the start procurement procedure, and we already done the RFI for the OFP2. And so currently we are describing the RFC, and very soon we will publish the RFC. And so the OFP was a top machine in the HPCI second tier system. And so we would like to keep our new system will be the second class of the Japanese supercomputer system. So we would like to inherit from the philosophy of the Oakforest-PACS to design the Oakforest-PACS. So the support for the very wide range of users and also large scale applications continuously. And also we would like to develop new field of users, so like AI for HPC, AI for science. And also the important thing, so the co-design with applications. Okay, so this is almost same things. So we already have a experiment like this kind of approach. So using the Wisteria BDX01, as Professor Nakajima mentioned. And also the University of Tsukuba side, they also have a very similar type of systems named Cygnus and Pegasus. Yeah, actually, it's a different system, but Cygnus is extreme computing part, and the Pegasus supports the big data part. So we almost shared this philosophy, and also that we are now performed this kind of experiment and experimented using these systems. And also we are recently we are facing the power energy crisis. So carbon neutrality and also the power efficiency are very important things. So we are going to shift the GPU for the most of the computer resources, but we need still the small portion of the CPU only node to support very traditional users. Okay, to decide the Oakforest-PACS 2 architecture, we asked pre-benchmark for the each accelerator vendors, actually GPUs. So we have over 3,000 users for Oakforest-PACS, and so we, of course, we promote our new system, but we need to demonstrate that how much good performance to utilize the GPU clusters in the newer system. And also we also support this number of users and also encourage to perfectly migrate from the many core type system to GPU clusters. So we asked GPU vendors pre-benchmark, actually the AMD, Intel, and the NVIDIA. And so we asked how much easier the porting from the existing code to the GPU part using the OpenCC or OpenMP, this kind of directive-based language, or the standard language support in the Fortran, newer version of Fortran or C++. And also the we can use the so CUDA, heap, SQL, or very basic level of languages. So, okay. Yeah, so this is a benchmark list. We asked 7 benchmarks as a benchmark, pre-benchmark to vendors from the almost 1 year before, and two kind of categories. So one is just written by the for the many core or multi-core, suitable for the many core or multi-core description using the OpenMP and the MPI. And another one is already a GPU ported programs using the CUDA or some GROMACS is a very popular one. And so this application already applied to the various kind of GPU architectures. And also the Salmon already introduced OpenCC directive-based language. So the as a result, so the we selected NVIDIA GPUs. So the reason is here. So the result of the performance of the benchmark, and also the ease of the porting effort, and also support environment. So this means the technical support from the vendors is sufficient or not, and also the ease to the Fortran support. So in terms of these points, so that we selected NVIDIA GPUs for the Oakforest-PACS 2 architectures. And so we are now porting, start porting, and so we call special support for the big users group, and also community code providers. So totally the 16 groups. And so we, and also the NVIDIA staff support this kind of porting effort. And also the other users, for the other users, we support minicamp tutorial, or directly we consult these users, and also that we provide several tutorial materials. Okay, so this is also design for the consideration point for the design of the OFP2. So this is a GPU node part. So we have several choices, so GPU architectures. So of course, the CPU part, we have several choices. So one possibility is Intel architecture-based host CPU. And also in this case, GPU will be connected by the PCI Express. And another choice is Grace Hopper. So this is ARM-based CPU, and also the H100 or successor connected by the NVLink proprietary interconnect between the CPU and the GPU. So originally the GPU, but in this case we can use CPU and the GPU, and also this provides us cache coherent feature. And so we would like to utilize GPU direct something. So the GPU direct for RDMA is already useful, but and also we would like to introduce GPU direct storage to provide us good performance for the file I/O from the GPU memory to the storage. So we would like to introduce local storage, local SSD for each node, and also the shared file system through InfiniBand. And so GPU direct storage can work both storage systems. And as I mentioned, smaller number of the CPU only nodes to support the traditional users. But of course we would like to promote the please go to the GPU node. So we don't have a much larger number of the CPU only node. Okay. So in this case, our user had high bandwidth memory, so MCDRAM. So in this part, we would like to introduce HBM to get good memory bandwidth. And also recently Sapphire Rapids with the HBM is available, and also the AMD EPYC Genoa has a much larger memory interfaces compared to the previous generation. For the storage, we would like to introduce hybrid mechanism with NVMe SSD for performance, and also for the capacity HDD. And so we would like single namespace for the storage. Okay, sorry over the time. So I would like to briefly say the co-design for the target application. We already tried to apply the study on the next generation accelerator for the file I/O and also the porting. And so this system area, I propose this project, and so we are going to establish and categorize GPU direct storage, or which is better, GPU direct storage or the traditional way. And also the second one is Professor Shimokawa, my colleague, lead this project, and so also they investigate how much easier to port from the traditional code to the GPU code. Okay, so this is just work in progress, but our private to use our private system, we investigate characteristics of the GPU direct storage using a local SSD. And so the data transfer manner is several kinds of data transfer manner can be considered. And so we tried evaluate several kind of bandwidths. And I'm not sure that this result is correct, or some incorrect settings, but yeah, some unstable behavior. But we are going to investigate this behavior. And so for the random access, also the quite strange behavior, but yeah, I asked the NVIDIA guides, this is correct or not. Okay, I tried the evaluation using the virtual machine guest OS to the raster file system using MDX, and even if the virtual machine, we can get better performance from the traditional way to the GPU direct storage, but gain is very small. Okay, and this is application phenomena. So that this is this result from the Professor Miki, my colleague, And so this is also astrophysics code. And so the observation that output is using the GPU direct storage. And so as you can see, the orange part is GPU direct storage is also very good performance thanks to the shorter latency than the traditional way. Okay, so this is a GPU porting part. So this is one example for the earthquake simulation seismic code or named OpenSWPC. And they tried to port from the OpenMP code to the do concurrent code, the Fortran standard parallelism. And they got that very good result. So for the difficult to compare the, so the 4 times 3.2 times first in the 16 GPU versus 4 GPU. So it is good scalability. Okay, so this is a summary of my talk. So Oakforest-PACS 2. So now we are now designing and perform the procurement. And so target is actually the October 2024 or later. And so originally target performance is over 200 petaflops, but almost gave us 200. So the budget restriction. But so we would like to keep the 150 over 150 petaflops for the GPU part, and also the CPU only node still prepared. And also we would like to install the second class of the from the next to the Fugaku system. So our system will be the support our community. And now we are going to the support the GPU porting of the existing applications. And also we are now procurement the prototype system with Mercury. So this system will be available at the October timeframe in this year. So this system can also support the porting effort for the Oakforest-PACS 2. So thank you very much. That's it.
Title of Chief Topic by Itoyori. Distributed parallel runtime global parallel.
Yeah, thank you for the introduction. And yeah, thank you for giving me a great chance to present my research here. I'm Shinpei Shina, a PhD student, and the title is like this. And so this is Itoyori called, this is Itoyori in Japanese. This is a fish called thread fin breams, which is delicious actually, but yeah, today's talk is not about the fish, but yeah, it's more about the threads. Okay. So this is a brief overview of the Itoyori runtime system, which is a global view task parallel runtime system. And it is implemented as a C++ library for distributed memory programming. All right. So first, I will give you a brief overview of this runtime system. And first, I will give you so yeah, Itoyori offers basically 2 components, which is nested fork join model and partition global address space, PGAS in short. The nested fork join model is a well-established parallel model, which found in the Silk or InterDPP or OpenMP tasks and so on. in this nested fork join model, programmers can create a lot of tasks regardless of the actual hardware parallelism, like how many cores in the hardware and so on. And the runtime performs dynamic load balancing for these numerous tasks. So the user don't have to care about the actual mapping of the tasks to the hardware cores. And because of this dynamic load balancing performed by the runtime system, so basically the programmers doesn't know which node executes these tasks. So we need a global view of distributed memory, which is often called the global ordered space, or PACS in short. All right, so with this, PACS model, tasks can access the global memory in a unified way from anywhere. And it also provides a software cache for global memory accesses to enhance the performance of global memory accesses. All right, so this is an overview, and the goal of Itoyori runtime system is to enable highly productive and scalable distributed memory programming. Okay, so here is a background, and as you know, so many workloads exhibit a very dynamic and irregular parallelism because of, for example, this dynamic shape of order and unbalanced tree structure. And people usually do a manual load balancing for these types of irregular parallelism, but it is usually cumbersome, and obviously the programmability and productivity is not very good. And we believe that the task parallelism, or more specifically fork join parallelism, is a good fit for these types of irregular parallelism. And from a viewpoint of hardware, automating this load balancing effort is very important. So because the programming cost is now very increasing, so even on shared memory, the memory hierarchy is becoming deeper and more complicated. And on shared memories, many parallel runtimes actually support the dynamic task parallelism. So however, on distributed memory, the support for the dynamic task parallelism is not very dominant, but instead MPI programming is still dominant in the HPC community. All right, so with MPI, so we should manually perform the load balancing and issue explicit communications between nodes to exchange the data. All right, so like this, the programming paradigm for the shared memory and distributed memory is very different, which often results in the two levels of parallelization, right? So for example, MPI plus OpenMP for developing a highly scalable application. So however, this is not good for productivity. So because of that, we pursue a unified programming model for both shared memory and global, not distributed memory. Sorry. So this approach is to extend the shared memory style fork join parallelism to the distributed memory, multi-node processing. And so far, so many distributed task parallel runtimes have been proposed and developed until now. And Itoyori has mainly two advantages compared with these existing systems. So first, Itoyori supports much more flexible threading capability, which enables which is enabled by dynamic thread migration across nodes. Okay, so in fact, most of the existing task parallel system is does not support fork join parallelism, but many of these systems support only the bag of tasks in which no task dependency between the tasks can be described. And instead, so it will support a more, shared memory like so Silk-like work steering, even on the distributed memory. And so, so software caching is another key feature of Itoyori. A combination of the fork join parallelism and the PACS model, often results in the poor scalability because of, fine-grained and redundant communication issued by its task. All right, so actually, so some PACS systems have a software cache, but so combining these dynamic migration of threads and software caching is, they did not investigate it by any other systems. All right, so here is the current development status of Itoyori runtime system. So Itoyori is implemented as a C++ library over the MPI3 RMA as a communication layer. So it has a very good portability, and so for the thread scheduling with a dynamic thread migration, very good scalability of more than 1,000 cores have been reported. So we also ported an existing shared memory application to the distributed memory using Itoyori runtime system. XFMM is an application which involves a very dynamic and irregular computation, which is based on the dynamic tree structure for managing the many particles, and which demonstrated 7.5 times speed up when scaling from a single node to 12 nodes. All right, here's a summary of the Itoyori runtime system. And so this is outline. And I will first explain the actual programming model of Itoyori. All right, so Itoyori offers a fork join model in which the programmer can dynamically fork parallel task and just join its completion. So it's very simple programming model, but it can express many types of parallel algorithms. And one important thing is that so parallelism can be arbitrarily nested. So some parallel recursive divide and conquer algorithms can be easily expressed by this fork join model. So in this program, the user can express, the user can spawn these two tasks and just join them at a time. All right, so many tasks are created and they have some task dependencies, and this can be expressed as a task dependency graph like this. And these tasks are dynamically scheduled to the hardware cores by maintaining these task dependencies. All right, so let's see the actual programming example written in Itoyori runtime system. So this is a parallel merge sort algorithm in which the input array is recursively divided into two parts. Right, like this. And these two child tasks are computed in parallel recursively until some threshold is reached here. All right. So we note that these threads can be dynamically migrated to other nodes for load balancing at these fork join calls. So the access to the local variables in other threads is not allowed in this programming model, but we can share some global memory by allocating the global object from the global heap managed by the PACS layer. So in this program, the pointer. So pointer is actually pointing to the global memory. And as you see, this pointer is just raw virtual address managed by the Itoyori runtime system. Okay, so but we cannot directly access to the global address space without calling this check out and check in calls, which is a special API calls for accessing the global memory address space. And so we explained more about the check out and check in calls here. And so the checkout call allows access to the global memory region specified by the programmer, and until the check-in call is made for that region. The user must specify the memory access mode here, read, write, or write. So if it is read or read write, then the system makes sure that the checked out region has the latest data. And if the memory access mode is read, write, or write, then the checked out region is considered dirty. So which means the region is modified by the programmer, and the system will ensure the global memory consistency. Okay, so here's a note. And while a memory region is being checked out, that region is guaranteed to be locally accessed by the programmer by using the same virtual address. Okay, because the threads can be migrated across the fork join calls, then we cannot keep checking out some memory regions across fork join calls. So the user must return the checked out region before any fork and join calls. And in addition, the same region can be concurrently checked out by multiple processes, as I explained it. And yes, the PACS layer has a software cache, and to promote the software caching, we employ a more relaxed memory consistency model. And it offers a sequential consistency for data race-free programs, which is called SC for DRF in short, which is also supported by many programming languages. So this model means that the programmers should write programs in the data race-free manner. So they do not have any data race-free in the program, then the memory order becomes a sequential consistency. Okay, so in theory, so as long as the program is written in the data race-free manner, then the programmers can concurrently access the same region by the checkout calls. Okay, so let's move on to the topic of the threading layer. So, okay, so before getting into the details, I will briefly explain what is work steering. So in work steering, each worker has its local task queue to store the local ready tasks. And basically, each worker pushes a task to the the local task queue and pops tasks from the local task queue. And if the task queue becomes empty like this, it tries to steal a task from another worker, which is randomly chosen. So this is called randomized work steering. And to extend this work steering to distributed memory, many researchers have investigated distributed work steering until now. So efficient RDMA-based work steering has been proposed, but so its execution model was just a bag of tasks in which no task dependency can be described. And some systems support the fork join model, but their threading capability was limited. So and after that, so the uni address scheme was proposed to efficiently migrate the threads across nodes. So this capability allows more shared memory like thread scheduling on distributed memory, for example, by suspending thread states and resuming these threads on another nodes. Yeah, for the purpose of load balancing. And so we recently reported that the union address scheme is highly scalable and can be scaled on more than 100,000 cores. And Itoyori also uses this union address scheme. Okay, so the next topic is a biggest layer, so which has a software cache. All right, so here's a figure, and I will explain why we need a software cache in this type of systems. So this represents a global tree of tasks, and each task independently access the global memory. And so, yeah, this is often the case in functioning programs that cross nodes access the cross data in the global memory. Okay, so however, because of the dynamic load balancing, the tasks may be scheduled to different nodes at runtime. So the user cannot guarantee that these tasks are scheduled to the same node or something like that. So because of that, so consequently, each task independently access the data it will use. So however, it causes a very fine-grained and redundant communication if the tasks are sufficiently fine-grained. So if we have a software cache managed by the runtime system, so we can aggregate communication among tasks that are scheduled on the same processor. And this is why we need a software cache for this system. And here is the overview of the software cache management. And there are 4 processes, and we are focusing on the process 1 here. Yeah, and first, so in Itoyori, so global memory consists of the multiple memory blocks of the fixed size, and the size of each memory block is a multiple of the page sizes because we utilize the virtual memory, some virtual memory tricks. All right, so. And so the physical memory blocks are assigned to each process like this. And these blocks are called home blocks. And the memory distribution policy can be specified by the programmer to determine which memory block is owned by which process. All right. And for each process, the same virtual address space called the local view is allocated and preserved. And this virtual address space is used as a global address space, and these virtual addresses are passed to the user. And this virtual memory address space may not have physical memory attached. And physical memory blocks are dynamically mapped to or are mapped from this local view dynamically. Right. So home blocks are basically directory mapped. So here is a home blocks, and these blocks are directly mapped to the local view of the corresponding virtual addresses. And so here's a cache blocks, which are used to store the local copies of remote memories, which are dynamically mapped to the local view on demand by the request from the programmers. And note that the cache blocks can be dynamically evicted by the runtime because the size of the cache blocks is fixed by the runtime. And when the checkout call is made, so here, then the cache blocks do not have latest data, then it will fetch the remote data from remote nodes. If the if we focus on this block, so this corresponds to this block. And so this, yeah, the memory owner of this memory block is process 2. So it will fetch the data from process 2 here. All right, so I'll briefly explain how Itoyori manages software cache, but because of the time limitations, I will just very briefly explain. And basically, the Itoyori performs a coherence cache actions, cache coherence actions when the work stealing event happen. So, for example, write back and self invalidations happen when there's a dependencies across nodes to ensure the global memory ordering. And by doing so, we can basically ensure the sequential consistency for data-less-free programs. All right, so next topic is evaluation. And so today, I will talk about the 2 evaluations. The first evaluation is about UTS. So which purely measures distributed work stealing performance. And the next is XFMM, which is a more realistic benchmark to evaluate the performance of global memory accesses. And we use the Odyssey supercomputer at the University of Tokyo. All right, so first I show the scalability of distributed work stealing. By using the unbalanced tree search benchmark. So in this UTS benchmarks, unbalanced tree is traversed in parallel to count the total number of nodes in the tree. But so it does not involve any global memory accesses in this benchmark to purely measure the load balancing capability. All right, so this figure shows a very good scalability of Itoyori's threading layer, which achieved a very great scalability of more than 100,000 cores. So all right, so work stealing alone performs very well. So the question is, what if we combine it with a PGAS or global memory addresses, global memory accesses? And for this case study, so we ported the fork join implementation of XFMM to distributed memory using Itoyori. The original fork join implementation was written for shared memory, but if we add some minor modification to the program, then it will run. It can run on the distributed memory. So we note that the entire parallel algorithm was not changed by this porting task. But only a minor modifications was made. If we use the MPI for this purpose, that entire parallel program should be modified from the parallel algorithm level, but it did not happen while we ported this application. And this is a result, and this result shows that Itoyori performs, and Itoyori scales very well, and it achieved a great scalability on multiple nodes. And so by comparing to the no cache version, so software caching does a very good job by improving the performance by up to 6 times. And for comparisons, we use the original MPI implementation of XFMM. So which uses different parallelization scheme for distributed memory, while within the shared memory, the same fork join parallelism is used in this MPI version. The MPI version often runs faster than Itoyori, but Itoyori performs competitively overall. Not that the Itoyori version uses global and unified fork join parallelism across nodes, which has much higher productivity than the MPI version. So this result demonstrates that Itoyori strikes a very good balance between the productivity and performance in this case. So here's a summary. And I will talk about our future work. And our future work includes improvements to the task scheduler. Currently, the randomized work stealing, which is just a very naive implementation, is used for task scheduling, but it is not good for deep memory hierarchies on the distributed memory. So previously, we have investigated the locality-aware task scheduling algorithm, which is originally designed for shared memory, which is called ATWS. And this can we believe this can much improve the performance on distributed memory. Thank you for listening.
Okay, so this is the end of the 42nd ASE seminar. So thank you very much for all speakers and also participants from on-site and online. Yeah, actually, so in recent several months, I attended on-site or hybrid meeting like this. And I noticed that we have more discussions than before. And I think we really wanted to do this. And we are very happy now. And it's very nice to continue these situations. And hopefully we have more visitors, especially international visitors, to hold the next ASE meeting. And also, I'd like Jonathan to be back before 2030. Okay. Okay, thank you very much. And so have a nice day.